One key point of this lesson is that location within the cloud network makes a difference in latency. In general, there's a direct trade-off. The more distributed elements are in your design, the more tolerant the system will be of outages. However, there are real performance limitations because the round-trip time is much slower between distant elements, and there are expense considerations for egress traffic. The critical technology to implementing intelligent traffic management in the design is load balancing. Fortunately, the platform offers a very robust set of load balancing services that are optimized for different circumstances.
So, network configuration for data transfer within the service, all is going to focus on location, load balancing, and caching. So the location of resources within the cloud within the cloud network, I should say, is very significant. So when you take a look here at, a million nanoseconds is 1 millisecond, depending on what network you choose. If you're going to choose, say, a 2 kilobyte packet over a 1 gig network, you can do this in 0.002 of a second. Now, what about a round trip within the same data center? Well, Google's data centers are pretty fast. You can get away with 0.5 millisecond, sometimes even faster, depending on the design. Now, what if you wanted to send something across the world from, say, California to the Netherlands and back? Well, that could be upwards of 150 milliseconds. Yes, even that is considerably fast due to Google's global fiber network. However, these are design considerations you need to take place, especially if you're looking at the perspective of the user or your specific application. So remember, no more than 6 to 7 round trips between the Europe and US per second are possible, but approximately 2,000 per second can be achieved within a data center. And these are important generalizations to understand whether it's time to push data closer to the user or actually locate your application in multiple different data centers themselves. So the technology that allows you to control the network location of resources used by your service is going to be called load balancing. Now, load balancing in our world is a little bit different. So basically what it does, it's getting user traffic to the application servers with capacity in the closest region to that customer. Unless, if you have no load balancing, sometimes it's going to be internal distribution of traffic across, say, multiple servers inside of your application infrastructure. It can also trigger auto-scaling, but we also provide global load balancers, and that gives you a single external IP address that can locate, or I should say, that can send traffic to any geographic location that's closest to your individual user. We offer many different kinds of load balancing services, and they're each optimized for each different use case. So first, let's take a look at our global load balancers. Now, by a global load balancer, you get a single external IP address that allows you to literally route your traffic to multiple regions or data centers where your applications might exist. Now, it'd almost be kind of silly to have one physical data center. Say you chose a single region in the U.S., and you put a global load balancer on it. Well, all the traffic would be sent there anyway, so perhaps you'd only be doing that for future proofing because you'd want to expand that. But if we take a look at the types of load balancers we have an HTTP, HTTPS global load balancer, and in this case it runs both IPv4 or IPv6 externally, but we still only offer IPv4 down to the VMs. But what also happens here is the certificates are terminated at the load balancer, so this allows entry from any location and you don't have to host the certificates on the individual VMs. Now, if you're not using HTTP, but just simply SSL, we can simply act as a proxy, but still offer SSL certificates as opposed to web-based certificates. And then we have a global TCP proxy. So this provides intelligent routing to wherever your application may be around the world. Now, we also have network and internal load balancers. Now, these typically run at, say, layer 3. They include things like session affinity and connection draining. So in case if you're scaling up an individual cluster as a result of network traffic, we can maintain those connections before actually telling the servers to start to shut down. We also maintain health checks, so this way we can determine, are these servers up and healthy? So oftentimes you'll have a combination of global load balancers and internal ones, because these will determine the growth or shrinkage of your individual clusters. Now, the internal load balancers basically are designed for back-end services. So this way they can communicate on the internal IP address as opposed to a fixed external IP address that we provide. What also you don't always see with our global load balancers is you get a lot of denial of service protections and some other security features in which we monitor traffic for any type of, I would say, unwanted type of traffic from the internet. So with this menu to choose from, you need some kind of decision tree. First of all, is the traffic external? Well, if it's not, an internal load balancer is usually ideal. Now, is it web-based traffic? Well, then we have our HTTPS load balancer. If it's just encrypted, well, SSL. And of course, if it's TCP traffic, well, here you can do our network traffic, our network load balancer. Otherwise, if you don't require pass-through, you can just simply use our TCP proxy. So depending on how your traffic needs to be managed or sent through, we pretty much have all the bases covered, which is great to see, because even when I first started here at Google, we only had some of the basic networking load balancing, didn't even have internal, and we only had HTTPS external load balancing. So you're going to see a lot of innovations. In fact, this is probably where Google is focusing the most, is particularly at the networking layer.